10, 9, 8, 7, 6.
Hello everybody, it is 3:30, which of course means it's time for one of our afternoon STEM shows here at the Headwaters Science Center. I'm Ryan, and today I'm joined by Angel, who you've probably met a few times, maybe even saw a picture of if you were here early on our Waiting Soon screen. And Angel is a blue-fronted Amazon parrot. And if you were watching Wednesday, you would have seen Lee, our executive director, reading this book here that's called The Truth About Parrots. This was kind of a fun book, just a bunch of kind of fun illustrations and kind of interesting little facts, tidbits about a bunch of different types of parrots. And one of the things that I thought was very interesting in this book that they talked about, watch her poop on me in a second here, is it talked a little bit about the way that parrots kind of use and also perceive color. And so it talks about it in the, oh, there she goes. Talks about it as them using colors to find mates, talks about them using colors as camouflage. One of the things that's kind of a very common truth about parrots is that they have a lot of very vibrant colors to them. And there's lots of different types of parrots, but having all these different colors is one of the things that's very much true. And in particular, there's this little passage, kind of a little takeaway down here that's kind of separate from the rest that says, some parrots may be more beautiful than we'll ever, I tried to read it upside down, couldn't do it, than we'll ever know. Parrots can see ultraviolet light, which when combined with the colors we can see may reveal feather displays beyond our imagination. And so there's lots of light around us all the time, and we have a certain kind of subset of light that we can actually see, but there's light that exists that, you know, we as humans just can't really see with our naked eye. And that's true for everything, but everything that can see can't necessarily see the exact same, what we call spectrum of light. And so what this is talking about is that parrots can see in what we would call ultraviolet light. And so ultraviolet light would be light that has a really, really, really short wavelength. So it's light that is not visible to us, but is visible to parrots like Angel and other parrots. And so one of the things that's really cool that it also kind of talks about a little bit later, if I can find that page quick, is it talked about there's a little bit of a difficulty that comes with studying parrots in the wild. And part of that is because with parrots, the males and females tend to look very similar to one another, so it can sometimes be challenging to tell them apart. But there's a lot of evidence to suggest that that might be a human problem. That might not necessarily be a parrot problem, and that because parrots can see, you know, this extra kind of part of the light spectrum that we can't see, that in fact the males and females of different types of parrots might actually look more different to each other than what we can perceive. There we go. So less is known about lifespans in the wild because parrots are difficult to track for a number of reasons, and one of the reasons it cites is because females and males look similar to one another. But like I said, that's something that is assuming we're looking at them as people. Whereas Angel is a female blue-fronted Amazon parrot, and there's a lot of evidence to suggest that male blue-fronted Amazon parrots have patches in their feathers, basically, that are very reactive to ultraviolet light in such a way that they would be very visible to a female like Angel, and that the males tend to get selected for that. They demonstrate sexual selection with males that have these feathers that are more reflective to ultraviolet light. And so for Angel, all the male parrots look different from one another, even though we can't really see that ourselves. And so I think what I want to talk a little bit about, see if I can get Angel back onto her perch over here. Nothing up. Now I talk about how Rusty is my most reliable co-star I have in any of these. Angel is not. Angel's a diva. But just want to talk a little bit about how we sort of perceive color ourselves, and kind of talking a little bit about what eyes are and how eyes work. And so basically within your eyes you're going to have two types of cells that are very relevant in this conversation. You have what are called rod cells, and what rod cells are useful for is perceiving different levels of light. So rods are what tell you if it's bright out or if it's dark out, basically. And then you also have cone cells. And so we, as humans, have three different types of cone cells. We have cone cells that are receptive to red light, we have cone cells that are receptive to green light, and we have some that are receptive to blue light. And parrots are a little different because parrots have a fourth cone, and that fourth cone is what lets them see in the ultraviolet. The other thing that's kind of interesting about this is we don't have the same exact number of all three types. You know, we have red, green, and blue, but we don't necessarily have red, green. We don't necessarily have red, green, and blue in equal amounts. So in fact, humans, we have a lot more red receptors than we do green or blue receptors. And one of the things I like to talk about as kind of being illustrative of that is I have here a color wheel. I printed it off right before we went live, and I have a pack of markers. I took the black and the brown one out, but a pack of markers here that I just opened up too right before we went live. And something that's kind of interesting, maybe we can get a camera angle on this, is what I'm going to do is I'm just going to lay out these markers kind of where they would be on this color wheel. Then we can scooch the whole cart forward if we need to too. So I'll start with the red, so it's going to be right about here. Right about there, actually. Now I have green, and the green's going to be right about here. I have the blue, and the blue is going to be right here. And so like I said, these are the three colors that we have receptors for. These are kind of the pure colors for humans. Everything else that we see is mixtures of these colors. And so I'm going to bring in some other colors here. So, you know, very common ones, orange, yellow, pink, and purple is what I've got. Let's take a look at where these ones fall. So the pink, you know, sort of almost right in between the blue and the red there. The purple kind of in between there, even again, a little closer to the blue. The orange really close to the red. The yellow kind of right in between the green and the red there. And you might have noticed a lot more of those colors are on this side. You know, there's two in between red and blue that I've got. There's two in between green and red that I've got. I don't have anything in between green and blue. They didn't give me that marker that would go in between here. And so why is that? Because we are way, way better at perceiving differences in levels of red than we are at perceiving different levels of green and blue. And so a really small change in the red levels makes a much bigger difference to us. And I mean, we can see that even too, just like on here, like, you know, we can point them out. So yeah, that's red and orange and yellow and green and, you know, pink and purple and blue. You know, kind of call all that blue, I guess. It's kind of where I would put that. So that's the anatomy of our eye in action there. You know, Angel might see this, and Angel probably sees a lot more distinction in this area than what we would, because she has that ultraviolet sensor, and that would affect this area here. That would be the area where she's more sensitive in than we are. The other thing I want to talk a little bit about is I talked about how we, interestingly there, kind of started with green, blue, and red as our three colors that we started with. And those would be what we would call our primary colors. And you might be saying to yourself, hey, wait a minute. That's not the primary colors that I learned in school. The primary colors that I learned in school were red, blue, and yellow. And that's interesting because there's kind of two different ways that we can mix colors. And the way that we learn to mix colors kind of usually in school is doing what we would call subtractive color mixing. And what subtractive color mixing is things that you do with like paint or ink or something like that. And we can even just do a little bit of that here. I brought a plate out, and so if I take some yellow and I take some blue, be thinking about what color we're going to end up with when I stir them together here. Any blue out? It's pretty low. There we go. And I can take these with my little brush and I can stir them together quick. I got some red and some blue, and what are we going to end up with? Why, green, of course. And we can do the same thing with, you know, if we wanted to do our, I'll do blue again. Blue, and red, and I only brought one brush with me, so I'm going to use my finger for this one.
Or the other end of the brush.
There you go. We mix those together. eventually we'll get purple if we keep mixing. A little more bluey than purpley, but a little more blue in than red probably. So there you go. Like I said, that's probably the way you learn to mix colors in school. And of course, if we were to mix our other two, our yellow and our red, we would get orange. And so that works that way because the way that basically we perceive colors from things that don't emit light is we see what colors get reflected. And so for red paint, basically what happens is there's light that hits this paint and it absorbs most of it, and the only stuff it doesn't absorb is the red light, and so the red light then gets reflected back, and so we see what light gets reflected back. And so we could, there's actually an experiment that we can maybe try, take our red paint there, we turn our lights down, turn up our red, you might see it looks a little different depending on what kind of light we shine on it. We're doing this as a live experiment right here. So you could look at that and probably not even really be able to tell it's red, right? Because there's no light for it to absorb. The only light we're really seeing right now is red, and so the red paint in there doesn't particularly stand out. There you go. Good. We could do something similar with their yellow paint. Let's do a blue. With our blue paint, if we did the same thing, I bet the result's going to look a little bit different. Okay. So it gets a lot darker, basically, because again, the only light that's being shined on it is red light, and it's absorbing the red light, so it's not really reflecting any light back on us, so it got a lot darker. It's almost opaque now. And we're not completely dark in here. There's some white light being shown on it from above here, but what you saw is that basically got a lot darker. It's getting closer to black, basically, with what's happening there.
Yeah, interestingly enough, Ryan, what we saw was more towards the bottom of the bottle. So the closer it was to the light, in that case, the more purplish it was. So it gave us a lighter color than that opaque you were talking about. Yeah.
Yeah, and so that's subtractive color. Yeah, subtractive color mixing. Like I said, that's usually the color mixing they teach you in school is with the, like I said, because usually when we're learning, we're doing it with paint. And even with that, if we want to get into a little nook of, you know, what they teach you in school isn't quite exactly typically how it really is once you get past elementary school. Like I said, we usually teach it as red, yellow, blue. Really, the primary colors that we typically use in subtractive color mixing when you're, you know, actually working within, like as a professional artist, it's typically going to be yellow, cyan, and magenta. But because magenta and cyan are colors that we're not that familiar with, we tend to simplify it, and so our spectrum is actually not perfectly equidistant from one another when we are making it. So we keep the yellow, but we, like I said, rather than being down here, we're over here, and rather than being over here, we're over here. So we miss out on a big chunk of this part of the spectrum, basically, with the primary colors that they teach you in school. So we would have a hard time making like this type of stuff if we were just working with these three paints. And so there is another type of color mixing that can happen though, what we would call additive color mixing, and that's sort of what we were doing over here. That's what this big circle is for behind me. So I'm going to turn our lights down again, and like I said, within, oh, is this what you're mad about? You dropped your net. And so within this, we have three knobs. So you saw me turn up the red knob before, but we also have a green knob and we also have a blue knob. And so we can adjust the various levels of light on this in order to make different colors. So for example, if we wanted to make, say, yellow, or one of our primary colors over there that we're missing, all I have to do is turn the red way up, turn the green way up, and there's yellow, with no blue. If we wanted to make magenta, the other, you know, sort of the one that we substitute red in for typically, we turn our red all the way up, we turn our blue all the way up, there's magenta, no green involved. And so if I wanted to do, the last one we're missing, oh yeah, cyan, that's all green and all blue with no red. And so like I said, this is additive color mixing. And so the way this works is basically you start from black, you start from nothing, and I say, ooh, I'm going to add all this blue in here. And we get blue if we just add blue. And I'm going to add a bunch of green in here, and now I have all this green, and we get cyan. And what would happen, do you suppose, if I were to add all the red in as well? What would we get? Tick, 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 tick. All right, let's give it a shot. White. And so in this, white is all of the colors mixed together sort of to their maximum. Whereas obviously in paint, if you want to make, mix all your colors together, you're not going to get white, you're going to get black, which I can't really do on here, but our equivalent of black would be this, basically, would be not having any light on there at all. And so we can make all kinds of adjustments. If we want to make orange, we can say, orange is a lot of red and probably a little bit of green and maybe just a smidge of blue. Something like that to get sort of an orange color. Whereas in that sort of color mixing, it would be, kind of equal parts red and yellow, basically, would be what gets us orange. But like I said, the thing that I wanted to kind of talk about here that's kind of interesting as far as how we can get, my table's on rollers, how we can get, these colors that we talk about as our primary colors, our cyan, our magenta, and our yellow, is that we can kind of simulate the subtractive element of it with a tool like this. And so I said yellow is, what happens with yellow is it absorbs all the light and reflects back yellow. And so we can do that. We can say, okay, we can pretend all of our light is getting absorbed except our yellow. So all the blue light is getting absorbed and all of the some of the red light and some of the green light are getting absorbed, and we can get to a yellow by absorbing different levels of the light that we have on here. I think it's kind of neat. Another thing I have that kind of works in tandem with this is I have these guys. And so these are what we would call translucent, so you can kind of see through them. It's a little obstructed, but light can pass through them, even if you can't really see through them that great. And these are magnets, and we keep these out on the exhibit floor, of different colors. And so what I want to do is I'm going to throw these onto our light ring here. And I'm just going to fiddle a little bit with the colors, and I want you guys to kind of take a look at and sort of experience what happens to them as we adjust the light levels on them. So remember where all of them are. And again, we're going to kind of do some hypotheses here. So we're sitting on white light right now. And what would happen if I were to suddenly take away all of the blue light on this? First off, what color would our light be? And then, if we had that color light shining through these, what are they going to look like? This is kind of part two of that question. So the absence of blue light creates yellow. And you might have noticed that some of them change in a little bit different ways than others. It's kind of like, we saw our blue one getting kind of darker again, and we saw our orange and our yellow and our red all kind of more trending kind of closer to each other than what they were before. You can tell them apart a little bit easier in white light than you can in just the yellow light. They start kind of merging together. And similarly, our green one starts looking a little bluish in there too. But what if we were to take all the green light out now? So we're going to leave the blue out too. We're going to get rid of all the green as well. And so the color we're going to be left with is just the red light coming through. And what do we think these are going to look like in only red light? Angel's got some ideas. And you're seeing, I haven't even taken all of the green light out yet, and you're already seeing that like the orange and the yellow are almost impossible to tell apart at this point already. And as we get further and further into the red, these three that are kind of the three that are more on the red side of the spectrum when we're looking at our color wheel, pretty much is clear. You can't even tell what color they are anymore. Like I could shuffle these up and... Here, Lee. I have Lee behind the camera today. Which one's which?
I'm going to guess that the one that, I'm going to guess that's yellow. I'm going to guess that that one's the orange one, and the top one's the red one.
Yellow, orange, red?
Yeah.
Alright, let's see.
It's fine.
He's right. Wow.
And I'll tell you, the only reason I could guess it was that they just appear darker. The one that's on for us, the top of the screen, just looks darker. That's all there is. So I guess the red was darker than yellow.
Yep. And again, what we're basically seeing is that it's kind of more of a trick that's happening within our eyes than it is happening on the table here, where the only light, the way that we perceive these as being the color they are is because they reflect red light. And so if you take away everything that isn't red light, there's nothing to make them stand out relative to anything else around them. And so, like I said, they basically just end up looking kind of clear because they're just the same color as the light around them. It's the same way that, you could do this with a pane of glass. A pane of glass is basically a white version of this, and if you shine white light through it, you basically can't see it. It's basically just clear. Another interesting thing that's happening over here, and you'll remember when we did our blue paint on this, that our blue paint got very dark as well. And you'll notice this one has gotten a whole lot darker with only red light being on it, because basically it doesn't have any light to reflect back. This should be reflecting blue light back, but it doesn't have any blue light to reflect, so it just is just absorbing all the light that's going into it. Our green isn't getting quite the same thing, and that's probably a product of whatever process they use, whatever dyes they use to make the green, not being as pure of a green as our blue is, as pure blue. I mean, we can check this out too. Here, let's look at it in just blue.
And it disappears. The blue
the blue one basically gets clear again, just like these ones did in the red. The green one actually gets pretty clear too. So I think our green has a lot of blue in it, probably more so than it has green. Meanwhile, these ones are more easily distinct than they've ever been. Basically, you can tell them apart easier than they could in the white light, because they, like you said, are absorbing a bunch of blue light, and they don't really reflect blue light normally, and so they're absorbing everything or reflecting more, a broader part of the spectrum than what they normally would be. And one last trick I'll do for us here. So we can, and I guess I don't know if this is actually going to work through the camera or not. Let me know. But one thing we can do, and maybe Lee, if you want to come in close and tighter onto here, one thing we can do that's kind of interesting, and you'll see this every once in a while, sort of an optical illusion that you can sort of participate in, is if you look at a color for a really long time, your eyes sort of adjust to that color and will allocate energy to the cones basically in such a way that makes them more or less sensitive to picking up that color. Your brain is kind of constantly trying to equalize you out to perceiving things the way that humans are supposed to perceive them, but you can kind of trick it a little bit by messing with the type of light that you're exposing it to. So our brain wants to be exposed to white light. That's what it's used to, and it kind of always assumes that it's being exposed to white light because of that. And so if you expose it to not white light, it's going to adjust. And so let's do it let's do green. And so right now we have just green light coming out right here. And what we're going to do is we're just going to hang out, and we're just going to look right at this green for, call it, 20, 30 seconds, something like that. I'm going to stare at it. And what our eyes are doing now are saying, okay, this is the new normal. This is the type of light that we just exist in now. This must be white. And so it's fiddling with sort of the way our eyes are working right now to, accommodate all this green that it's getting. It's thinking it's overtuned. It's thinking it's oversensitive to green because of how much green it's perceiving. And so basically what it's doing is it's kind of turning down the sensitivity on our green cones. It's, you could sit there and look at this and look at this and look at this for long enough, and it would look less and less green to you. And you might be experiencing that already, where it doesn't look as green as it was when you started looking at it. And in just a second here, what I'm going to do is I'm going to turn up the red and the blue all the way. And so we're going to be looking at white light in just a second here. And what we'll experience is probably not going to look as white as what you might be expecting. So I'm going to turn them up right now. So we're looking at white right now. But I'm sure definitely to me, and potentially to you guys, like I said, I don't know how this translates through the camera, but I'm sure Lee can attest to this. It doesn't look very white, or at least it didn't right when I turned it over. It's already starting to adjust back for me, though, where it's starting to look more white. And what color did it look like to you?
Bluish violet is kind of what it's looking like. In fact, Ryan, there's even some stripes going across it.
Kind of like that?
Yeah, exactly.
So, what we saw was the opposite of green. They said we turned our green receptors way down, and as we talked about, the absence of green is magenta. And so when we look at just green for a really long time and suddenly, bam, we're looking at white, like I said, our brain has kind of adjusted itself to be less sensitive to green. And like I said, it kind of tricks ourselves into thinking it looks like magenta even though it's white. And we could do that with any of them. I mean, we could stare at the red for a long time, and when we turned it up, it would look like cyan. Angel, shush. I suppose she's probably having kind of a weird time with this, because like we said, she's a lot more, she's receptive to more colors than we are. This probably looks even more strange to her than what it does to us, adjust all this color adjustment that we're doing here. The other thing is that we have two different types of cells in our eyes. We have the cones that we've been talking about a bunch, but we also have those rod cells. And like I said, the rods are about sensing light levels, basically. So lots of rods basically means more light sensitivity. And I guess I don't have a ton to say about that. Parrots don't have a particularly notable number of rods. They perceive light and dark at a very similar level to what we do. But you could take something like a cat or an owl or something like that, something that lives at night. And one of the adaptions you will see in their eyes, they have way more rods. Domestic cat has something like 8 times as many rods in its eyes as a human does. I don't know what an owl has, but it's probably more than that even, I would guess. And that's a big part of what facilitates them being able to be active and see relatively well at night, is just having a lot more rods. But I think I've talked about all I want to talk about here. So visited with Angel, talked a little bit about ultraviolet light and how not all animals see light in all the same spectrums. We talked a little bit about the human eye and what colors we're good at perceiving. We talked a little about mixing colors and how it's a little bit different depending on kind of which end of the additive or subtractive kind of thought process you're coming from. And we talked a little bit about just like light levels too. So a lot of different topics all dealing with just light and color here. So if you thought that was interesting, we do these shows most days, Monday, Wednesday, Friday, and then Saturday, Sundays, kind of sometimes yeah, sometimes no right now. But Monday, Wednesday, Friday, generally, we're always doing these shows. So if this type of material seems interesting to you, you can tune in any of those days. It's basically a different educator talking about a different topic every day. So if you didn't like this one, tune in a different one. It'll be someone else probably. So check them out too. The Headwater Science Center is open 7 days a week. So we are open from 9:30 to 5 on Monday through Saturday. And then on Sundays, we are open 1 to 5. So you can swing by after lunch on Sunday. And like I said, we'd be happy to hear from you. So thank you guys for watching. This will be going up on YouTube. So if you heard something that you want to hear me want to play back, you can go and check it out on YouTube. It'll be up there pretty much as soon as we're done chatting here. But otherwise, thank you guys for watching, and we will see you on when we see you.